Imagine waking up tomorrow and someone hands you the keys to a factory. Not just any factory, a building so advanced that engineers wear full body suits just to walk inside it, where the air is filtered thousands of times cleaner than a hospital operating room, and where a single speck of dust smaller than a strand of hair can destroy a product worth millions of dollars. That factory cost more to build than most professional sports stadiums combined. In fact, it cost more than some entire countries spend on their national infrastructure in a year. And yet, somehow, it's one of the most profitable pieces of real estate on the planet. This is a semiconductor fabrication plant, a chip fab. And by the end of this video, you're going to discover the one hidden reality about these facilities that almost nobody outside the industry understands. A truth so strange that entire nations have gone to war footing over it, without a single shot being fired. Once you hear it, you will never look at your phone, your car, or your laptop the same way again. But let's start with the basics, because at first glance, this business looks almost impossible to understand. A semiconductor fab is where raw silicon gets transformed into the tiny brains that power almost everything in modern life. Your phone, your car, your refrigerator, fighter jets, missile guidance systems. Every single one of them needs a chip, and every single chip starts its life inside a building like this. Here's where it gets strange. Most people assume building a factory is mostly about machines and workers. Pour concrete, install equipment, hire staff, start producing. That's how you'd build a car plant or a clothing factory. But a chip fab breaks every one of those assumptions. Building one of these facilities can cost between $10 and $30 billion. Let that number sit for a second. $30 billion before a single working chip rolls off the line. Compare that to building a Tesla gigafactory, which costs a few billion, or a massive oil refinery, which might run $5 to $10 billion. A leading edge chip fab can cost 3 to 5 times more than either of those, and it becomes outdated within a handful of years. This is where most people are wrong about this industry. They think the value is in the chips. It's not. The real value, the real war being fought globally, is over who can build and operate these facilities at all, because almost nobody can. Right now, only a small handful of companies on Earth can manufacture the most advanced chips. Not dozens, a handful. Taiwan Semiconductor Manufacturing Company, known as TSMC, dominates advanced production. Samsung competes at the high end. Intel is racing to catch back up. And that's essentially it for cutting-edge logic chips below a certain size. Now think about this. Nearly every powerful nation on Earth depends on a tiny island called Taiwan for the chips that run their economies, their militaries, their hospitals, and their banks. That single fact alone should tell you this isn't just a business story, it's a geopolitical one. But we'll come back to that later, because first you need to understand who actually owns these facilities and what ownership even means in an industry this extreme. Ownership in the chip world doesn't look like ownership anywhere else. There are 4 basic models, and each one changes the entire risk profile of the business. The first is the pure play foundry model, used by companies like TSMC. These companies don't design chips at all. They simply manufacture chips designed by other companies for a fee at massive scale. Apple designs its chips. TSMC builds them. This separation of design and manufacturing turned TSMC into one of the most valuable companies on the planet because it lets every chip designer in the world use the same advanced factories without having to build their own. The second model is the integrated device manufacturer, or IDM. Companies like Intel design their own chips and manufacture them in their own fabs. This gives total control over quality and secrecy, but it also means carrying the entire $30 billion burden alone, with no outside customers to help spread the cost. The third model involves government ownership or heavy government backing. Countries like China have poured enormous state funding into domestic fabs because losing access to foreign chip supply is considered a national security threat, not just a business risk. And the fourth model is joint venture ownership, where multiple companies or even multiple governments share the staggering cost of a single facility because no single player wants to absorb that much risk alone. Here's the twist most people miss. Even when a private company technically owns the fab, governments often quietly control its fate through subsidies, export restrictions, and trade policy. In the United States, the CHIPS Act committed tens of billions of dollars specifically to attract fab construction onto American soil. Europe and Japan have launched similar programs. Ownership on paper is corporate. Ownership in practice is deeply tangled with national interest. So what are you actually buying if you own one of these plants? At first, this seems simple. You're buying a building and some machines, right? Until you discover what's actually inside. You're buying land, yes, but it has to be near abundant, ultra-clean water and a rock-solid power grid because a single unstable second of electricity can ruin an entire production batch. You're buying a building, but not a normal one. It's a vibration-isolated structure with clean room environments, classified at levels thousands of times more filtered than a surgical room, because even microscopic contamination ruins a chip. Then comes the equipment, and this is where the real money disappears. The single most critical machine in advanced chip manufacturing is an extreme ultraviolet lithography system, or EUV machine, made by a Dutch company called ASML. A single one of these machines can cost between $100 and $200 million. Not the whole factory, one machine. And here's the part that shocks most people. There is currently no other company on Earth that can build these machines at the cutting edge. ASML holds what amounts to a total monopoly on the most advanced lithography technology in existence. If ASML stopped selling tomorrow, the entire trajectory of advanced computing would stall almost overnight. A modern fab needs dozens of these machines, alongside hundreds of other specialized tools for etching, deposition, and testing. You're also buying licensing rights to chip designs, manufacturing process technology, and intellectual property that took decades and untold billions to develop. You're buying long-term supply contracts for ultra, pure chemicals and specialty gases that barely exist outside this industry. This is where everything changes from buying a factory to buying a piece of a fragile global supply web that spans dozens of countries. Now let's talk about what it actually takes to get this thing built in the first place, because the startup costs alone would bankrupt almost every company on Earth. Constructing a single advanced fab typically costs somewhere between $10 and $20 billion for the building and core infrastructure alone. Add the equipment, and total costs regularly reach $20 to $30 billion for a single leading-edge facility. Construction can take 3 to 5 years before the plant produces a single usable chip. During that time, the company is spending staggering sums on permits, environmental approvals, and specialized construction labor trained specifically for cleanroom-grade building standards. Financing this typically requires a mix of corporate debt, government subsidies, and in some cases contributions from major customers who want guaranteed future chip supply. But here's what almost nobody realizes. Even after the building is finished, it can take another 12 to 24 months just to get production yields high enough to be profitable. Yield refers to the percentage of chips that actually come out working correctly. In early production, yields can be painfully low, sometimes below 50%. Every failed chip is still a chip that consumed expensive materials, electricity, and machine time. This tiny detail costs companies billions in silent losses before a fab ever turns a real profit. So once it's finally running, how does a chip fab actually make money? The primary revenue stream is straightforward: manufacturing chips for customers, whether that's a foundry charging design companies for production or an integrated manufacturer selling finished chips directly to device makers. But that's only one part of the story. Secondary revenue comes from specialized packaging services, testing services, and design support that many fabs now offer alongside pure manufacturing. As chips become more advanced, some manufacturers charge premium fees for cutting-edge process nodes, since only a handful of companies can produce them at all. Then there's hidden revenue, and this is where the real profit machine lives. Long-term supply agreements often lock in massive customers years in advance, sometimes requiring upfront deposits just to reserve future production capacity. Apple, for example, has reportedly committed billions of dollars in advance payments just to secure guaranteed manufacturing slots at TSMC. This isn't just selling a product, it's selling scarcity itself. Recurring revenue comes from the fact that once a chip designer commits to a specific manufacturing process at a specific fab, switching to a competitor is enormously expensive and risky. This creates incredible customer loyalty, almost like a subscription service, except the subscription is worth tens of billions of dollars a year. Now think about how the money actually flows through this entire system, because it's stranger than any typical supply chain. Silicon wafers arrive from specialized suppliers. Ultra, pure chemicals and gases arrive from a small number of qualified vendors. Lithography machines arrive from ASML, sometimes with waiting lists years long. The fab transforms raw materials into finished wafers containing hundreds of chips each. Those wafers get shipped to packaging facilities, often in different countries, before finally reaching the device makers who put them into your phone or your car. But here's what almost nobody realizes. This entire chain can span 15 or more countries before a single finished chip reaches a consumer product. A disruption anywhere along that chain, a shipping delay, a natural disaster, a political conflict, can ripple through the entire global economy within weeks. This is exactly what happened during the pandemic-era chip shortage, when car manufacturers were forced to pause production lines because they couldn't get simple chips worth just a few dollars each. Let that sink in. A car worth $40,000 stuck in a parking lot because of a missing chip worth less than a cup of coffee. That's how fragile and powerful this industry really is. Now let's talk about the expenses, because keeping one of these facilities running is its own kind of financial nightmare. Labor costs are enormous, not because fabs need huge headcounts, but because they require some of the most specialized engineers and technicians on the planet, many holding advanced degrees in materials science, physics, or electrical engineering. Electricity consumption is staggering. A single large fab can consume as much power as a mid-sized city. Some advanced facilities require hundreds of megawatts of continuous power, and any interruption, even for a fraction of a second, can destroy an entire batch of chips mid-process. Water consumption is equally extreme. Advanced fabs can use millions of gallons of ultra, pure water every single day for cleaning and cooling processes. This is exactly why fabs are almost always built near reliable water sources, and why droughts have occasionally forced production slowdowns in places like Taiwan. Maintenance costs are relentless, because the machines inside are so precise that even minor calibration drift can ruin production. Taxes, insurance, and debt servicing add another enormous layer, especially since so much of the initial construction is financed through massive loans or government-backed agreements. And then there's technology spending. Because in this industry, standing still means dying. Every few years, a new generation of smaller, more powerful chip technology emerges, and fabs that fail to upgrade quickly lose customers to competitors almost overnight. But we're still not finished, because beyond these expected costs, there's a whole layer of hidden costs that can quietly destroy profitability. Compliance and regulation costs are massive, covering environmental standards, chemical safety rules, and increasingly, export control laws that restrict which countries can receive advanced chip technology. Legal risks include intellectual property disputes, since chip designs represent some of the most valuable trade secrets in the world. Environmental risk is a serious concern too. The chemicals used in chip production must be handled and disposed of with extreme care, and any environmental violation can trigger massive fines or even forced shutdowns. Operational risk includes the ever-present danger of a single production error contaminating an entire manufacturing line, sometimes costing tens of millions of dollars in an instant. And this leads to an even bigger problem, geopolitical risk. Because advanced chip technology has become classified almost like a weapon of war. Export restrictions between major powers can instantly cut off access to critical equipment or customers, turning a purely economic decision into a matter of national security within days. So after all of that, how profitable is this business really? Margins vary significantly depending on how advanced the manufacturing process is and how efficiently a fab operates. Leading foundries often report gross margins in the range of 45 to 55% on their most advanced chip production, which is extraordinarily high for a capital-intensive manufacturing business. But those margins can shrink dramatically for older, less advanced processes facing heavy competition. Cash flow in this industry follows a brutal rhythm. Massive upfront investment, followed by years of ramping production, followed by a relatively short window of peak profitability before the next generation of technology arrives and the cycle begins again. Break-even points can take several years to reach, and return on investment depends heavily on whether a company can maintain its technological lead long enough to recoup those enormous upfront costs before its equipment becomes outdated. This is exactly why so few companies attempt to compete at the cutting edge. The financial risk is almost unimaginable, and the timeline for profitability is brutally long. Which brings us to why some of these businesses fail entirely. Competition is fierce at the highest levels, and falling even one generation behind in process technology can mean losing your most valuable customers to a rival almost overnight. Bad management decisions, especially delayed technology transitions, have famously cost some historic chip giants their leadership position in the industry. Wrong location decisions matter enormously too, since fabs require stable power, abundant clean water, and reliable infrastructure, along with proximity to skilled engineering talent. Excessive debt taken on during construction can crush a company if production ramps slower than expected, and broader economic downturns can suddenly crash demand for chips across entire industries at once, leaving fabs running at a fraction of their capacity, while fixed costs continue piling up regardless. Now let's look toward the future, because this industry is evolving faster than almost any other on Earth. Artificial intelligence has completely reshaped chip demand. AI accelerator chips, the specialized processors that power machine learning systems, have become some of the most valuable and expensive chips ever produced, with certain advanced AI chips selling for tens of thousands of dollars each. This has triggered an unprecedented wave of new fab construction specifically dedicated to AI-related chip production. Automation inside the fabs themselves continues advancing too, with increasingly autonomous systems handling wafer transport and quality inspection, reducing human error in processes where the smallest mistake can be catastrophically expensive. Industry trends point toward continued geographic diversification as governments push to build domestic chip manufacturing capacity rather than relying entirely on a small handful of facilities concentrated in East Asia. This shift is reshaping where billions of dollars in future investment will flow over the coming decade. And now, finally, we return to that hidden truth we promised at the very beginning. Remember, we told you that once you understand semiconductor fabs, you'd never look at your phone, your car, or your laptop the same way again. Here's why. Nearly the entire modern global economy, every advanced military system, every AI breakthrough, every smartphone, every electric vehicle, depends on manufacturing processes so precise that they can only be performed inside a small number of buildings on Earth, using equipment made by an even smaller number of companies, most critically, a single company holding a near-total monopoly on the machines required to make the most advanced chips possible. This means the true center of global economic and military power in the 21st century isn't oil, and it isn't gold. It's measured in nanometers inside clean rooms most people will never see, built by a handful of companies whose names most people can't even pronounce. That's the hidden reality almost nobody talks about. The next time you unlock your phone, remember that the tiny chip inside it represents one of the most concentrated, most fragile, and most fiercely contested pieces of infrastructure in human history, and the company that made it possible might just be one of the most powerful entities on Earth that you've never heard of.